So in this video, I'm going to introduce the basic idea of a derivative, which is a way to go about computing the slope of a graph and also the rate of change of the function. Although in this video, we'll be talking a lot more about slope. As we have already laid down the foundation for pretty much this entire topic in previous videos, I'll just go through it quickly and remind you. Let f be a function with a value x0 in its domain for every single non-zero increment of x, so that x0 plus this increment is also in the domain of f. The expression f of x0 plus the increment h minus f of x0 divided by h is called the difference quotient of f at x0 with increment h. Now, written that way, it's not very familiar, but if you just replace x0 plus h with x sub 1, it's just equivalent to the slope of a line through two different points. And it's also actually the average rate of change of the function over the interval from x0 to x1. So if you recall, the way it came about, at least one way, was that we were after the slope of the graph. We found a point on the graph, x0 comma f of x0. We then increased the x value of the point a little bit and found the corresponding point on the graph. From there, we have a change of x and a change in y. We found then the slope between these 2 points to get the slope of the secant line. And then, after that point, we then take a limit by letting the increment of x, in this case being h, we just let that go to 0, which forced the point Q to move towards point P, so that the secant line became more like the tangent line. So in the end, the limit equals the slope of the tangent line at that point of tangency, which means it's also the same as the slope of the curve. So as a simple example, given the function f of x equals 1 over x, let's find the equation of the line that is tangent to the graph of f at the point whose x-coordinate is 2. Well, to find that particular answer, I would of course need to know what is the corresponding y-coordinate. So the x-coordinate of this point is 2. The y-coordinate is found just by evaluating the function at that x-coordinate. In that case, that's f of 2. So that's just 1/2. So I now know the point of tangency. That is the point that's on the graph and is actually on the tangent line at the same time. So then the point is 2 comma a half. So I now need the slope. Well, the slope is found by then going and finding the limit as h approaches 0 of f of x0 plus h minus f of x0 all over h. And that is the limit as h approaches 0 of f of x0 here is just 2. Our increment is h. Then you have minus f of 2, because that's x0, all over h. That would then equal the limit as h approaches 0 of, evaluating the function at 2 plus h, that would be 1 over 2 plus h, minus, and then evaluating the function at 2 gives me 1 over 2, divided by h. That then equals the limit as h approaches 0. If we add the fractions, you would get 2 minus a 2 plus h in the numerator and 2 times 2 plus h in the denominator. And I'm dividing this entire thing by h. So I'll do that division right here by putting an h there. That then would be the limit as h approaches 0 of, in the numerator, you'd have a 2 minus a 2, that would be, well, nothing. And then you'd have minus h. So you have minus h divided by 2h times 2 plus h. We notice there's a common factor of h here, so I'll cancel that. I'm allowed to do that because h actually isn't 0, it's just near it. So that's negative 1 over 2 times 2 plus h. And that is a continuous function of h. So because of that, I can certainly just evaluate this limit by plugging in 0. So we just plug it in. We get negative 1/4. So that's the slope. So that then means that to find the equation of the line, I could write y minus the y-coordinate of the point, which here is a half, is equal to the slope, which is negative 1/4, times x minus the x coordinate of that point, 2. And that's it. That's the answer. If you feel compelled to go and solve for y, you can, but you really shouldn't, actually. That's a habit you were taught maybe before this class, and you really shouldn't. There's good reasons why you want to leave it that way. Well, now in that previous example, I found the slope of the graph essentially at the point whose x-coordinate is 2. But I could have picked any x value as long as I didn't pick 0. So why don't we just do that? I'm going to find the slope of the graph now at any single point on that particular graph, just by looking at the x value of that point. To do that, the slope is then equal to the limit as h approaches 0 of f of x naught plus h minus f of x naught. That would be all over h. Now, since you just saw the previous example, I'll skip ahead here. This is then the limit as h approaches 0. You'd have 1 over x naught plus h minus 1 over x naught further divided by a h. And that would then equal the limit as h approaches 0 of, adding the fractions and simplifying them this time, doing it quickly, you would get a minus h all over x naught times x naught plus h, and that's still divided by h, so I have to put a division of h here like I did before. I could then go and cancel the h's since the h is not 0 to get the limit of negative 1 over x naught times x naught plus h, and this is a continuous function in h because x naught right now in the limit is not changing, it's a constant. So I can find this limit by just plugging in 0 for h to get negative 1 over x naught squared. And that gives me the slope of the graph at any single point. All you have to do is give me the x-coordinate of that point. One of the great reasons that algebra has been so effective in our careers is that it's able to cut down a lot of the things that don't matter and boil a problem down to almost a mechanical process that we all agree upon in the end is the right answer. So then the work you just saw might feel, well, that seems reasonable. So I know the slope at any single point on that graph. But it doesn't, unfortunately, it lacks that connection to real world problems, or at least what we accept as reality. And in this case, seeing is believing. So let's go check out the graph of this function. And let's see what happens to the slope of the graph as we just take a point on that graph and we let the x-coordinate increase without bound. Now you remember what the graph of this function looks like. The graph of 1 over x looks kind of like this. And it has a horizontal asymptote here at y equals 0. Well, just take a single point on that graph. The x-coordinate would be x naught. The y-coordinate, I honestly don't care. It's just f of x naught. And that's where f of x is equal to 1 over x. Look at the slope, though, here. To find the slope, envision that tangent line. Now, this slope is certainly negative. But if you let the x-coordinate increase without bound, you should get that the point moves, but the tangent line, of course, actually is also at the same time changing. And looking at these two slopes, both slopes are negative. But see how the line's becoming more and more like a horizontal line? That means that the slope is tending towards 0. And in fact, if we take the limit as x naught goes to infinity of the slope that depends upon that x value, you wind up taking the slope, which was negative 1 over x naught squared, and taking the limit of that as x naught goes to infinity, and we know that limit is 0, which is exactly what appears to happen when you look at the graph. So remember, there's another way to interpret the difference quotient. It just represents the average rate of change of the function over the interval from x naught to x naught plus that small change. Well, if again we use the limit, this average rate of change would then be called the instantaneous rate of change. So the limit as h approaches 0 of f of x naught plus h minus f of x naught all over h is called the instantaneous rate of change of the function with respect to x at x naught. As an example, let's go do a problem that is similar to something I've already done. So we have a rocket that's taken off from ground. the height of the rocket in feet is given by 16t squared, where t is the amount of time that has passed since liftoff. I want to know the rate of change of the rocket's height 2 seconds into flight. So that will correspond to a feet per second. So it's a type of speed. Also notice no time is passing. It's exactly at the 2 second mark. So this rate of change is an instantaneous rate of change. Well, to do so, I would find the rocket's position 2 seconds, a little bit after 2 seconds. I would find the rocket's position exactly 2 seconds into flight. That would then give me the distance traveled, and I would divide by how much time has elapsed. By taking the limit as h approaches 0, I would then be taking the limit of an average rate of change. That is the instantaneous rate of change. So this then equals the limit as h approaches 0 of, I'd have a 2 plus h squared times 16 minus, that'd be a 16 times 2 squared, and that's all over h. So I have to find that limit. So that is then equal to the limit as h approaches 0 of, I'm going to cheat a little bit and take out the common factor of 16, so I don't have to deal with it. Then I'd have 2 plus h squared minus 2 squared, and that's all over an h. Well, now that is equal to the limit as h approaches 0 of 16. Again, just because I'm trying to cheat and try to get through it quickly, notice that that's actually a difference of squares. So I can instantly factor that. So the first factor would then be 2 plus h minus 2, which is h. And then I'd have 2 plus h plus 2. That'd be h plus 4. And that's all over my h. Well, in the limit, though, the h is not 0. So I can cancel those h's, giving me 16 times h plus 4. That then is a continuous function of h. I can then just plug in 0 to get 16 times 4, which is 64. And in terms of the units I mentioned, that would be in feet per second. Notice it's a little different from what I did before with graphs and slopes, because there are no units. Here, though, when you're talking about rates of changes, it's always a change of one quantity, in this case height, over a change of another quantity, this case time, and you would then take a limit of it in order to get the quantity you were interested in. So this then means that the n units must be in feet per second. Well, now, we've now computed this limit twice for two different problems. Of course, we use different variables here and there and different names of functions. But in the two examples you've seen, I've given you a certain value in the domain, and then we computed this limit. And this limit happened to be connected to two different types of problems, slope of graph problems and instantaneous rate of change problems. So clearly, the limit process itself is fairly important. So, from now on, if we ever do this process for a function at a certain x naught, we are going to associate that with a certain sequence of symbols so that we remember what we're computing, and that way we can investigate it later. So, the derivative of a function f at a point x naught, and of course y naught if we actually need it, is denoted by f prime, that's what the little dash there means, f prime of x naught. And it happens to equal the limit that you see, provided the limit exists. Let's look at another example, this time one that focuses on the connection between the slope of the graph and the rate of change of the function. So we have an experiment where we're growing yeast cells and we're counting the number of cells p after so many hours, let's say t. Well, the picture I give you then gives you the relationship between time and the number of cells. So in that context, what would p prime of 2 mean? Well, the derivative corresponds to a change of one quantity over a change of another. In this case, it's a change in the number of cells over a change in time. That would be an average rate of change. That gives you a hint then of what the units should be. P prime of 2 then gives you the number, or the rate of cell growth per hour after or if you want, not after, but exactly at 2 hours into this process. It tells you exactly how fast the population of cells is growing at that exact moment as a rate of cells per hour. So then which would then be greater, P prime of 2 or P prime of 3? Well, but P prime of 2 graphically is the slope of the tangent line at 2. So here's that line. Here's that line. And then here is then P prime of 3 being the slope of the line tangent at 3. Now looking at those two things, it looks like this one has a steeper slope. So I'd be forced to assume that P prime of 3 is greater than P prime of 2. So just in summary, these things all are talking about the same object. We're all talking about this particular computation, the limit of the difference quotient, as the increment is going to 0. So it's the slope of the graph of the function at the x-coordinate, whose x-coordinate is x0. It's the slope of the tangent line to that curve at that exact same point. That shared point is called the point of tangency. It's also the rate of change of the function with respect to x when x is x0. It's also the derivative f prime of x0 at x equals x0. And that gives you a basic introduction to what we mean by the derivative and the various different ways you can interpret it.